Today's lesson is called Complex Zeros and Fundamental Theorem of Algebra. We are going to be talking about the complex zeros of a polynomial of higher degree, meaning the complex solutions. That's what it means to be a zero. Well, the fundamental theorem of algebra says the polynomial function of degree n, like a fourth degree polynomial or fifth degree polynomial, has exactly n complex zeros. You see, this includes the real and the non-real. So dirty little secret, guys. Every real number is technically a complex number. Every complex number is written in the form a plus bi, where the a is the real part and the bi is the quote-unquote imaginary part. So a complex number is built up of a real part and an imaginary part. So every real number, like the number 2, is a complex number. 2 plus 0i, with the number 5. 5 plus 0i. Every real number is a complex number. So no matter what the degree of the polynomial is, that's the number of zeros it has. Complex zeros. Linear factorization theorem says any polynomial that has a degree bigger than 0, obviously, has precisely n linear factors. So a degree 5 polynomial can be split into 5 sets of parentheses that are all linear. Well, a is the leading coefficient, and it's right there out front. And f of x written with z1, z2, z3, z4, dot, 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 dot. Those are the complex zeros of f of x. Mathematicians use z for complex numbers. Those z sub I, those terms, z's, they're not necessarily distinct numbers. Some can be repeated. Remember, multiplicity. I will save you the pain of multiplicity of complex solutions, though. Don't you worry about that. So fundamental polynomial connections, but specific to complex cases. The following statements about a polynomial are equivalent if k is a complex number. Now, we've had this box before, but specifically we said if k is a real number. Now I'm saying if k is a complex number. X equals k is a solution or root of the equation f of x equals 0. K is a 0 of the function f. X minus k is a factor of f of x. All of these things basically say the same thing. The last time you saw this box and I said k was a real number, there was a fourth thing down here that does not exist for this. Can anybody remember what that was? One more thing that is true when k is a real number. They all mean equivalent things. That's missing from this. A solution is a root, is a 0, and x minus k is a factor. One important thing is missing. What do you think it is? It's x-intercepts. See, x-intercepts are normally zeros, aren't they? But that's only if the zeros are real numbers. You can't cross the x-axis at a complex number. That, by definition, is a place where you do not cross the x-axis. So good for you, yeah. So the thing that's missing is x-intercepts. We can't call complex solutions x-intercepts. Solutions that are strictly real, those are x-intercepts. Okay. Nobody in first period remembered, so congratulations. This says to write a polynomial function in standard form, identify the zeros of the function and the x-intercepts, because remember, a 0 is only an x-intercept if it's real. So it's telling us to write this in standard form. You know what? I'm going to go ahead and do them backwards. I'm going to do the zeros and x-intercepts before I find the polynomial in standard form, because you would use the linear factorization to find the zeros and x-intercepts. I'll go ahead and just list them right up here next to it. So for A, our zeros, those are everything that makes the inside of the parentheses equal 0. So x equals, in the first set of parentheses, it would be positive 2i. And in the last set of parentheses, it would be negative 2i. So the zeros are plus or minus 2i. Hey, look, both of those zeros are complex. So does it have any x-intercepts? No, it does not. That represents a quadratic that does not cross the x-axis. How did I know quadratic? because it's two sets of parentheses, two linear factors. And when we multiply those two linear factors, we will get a quadratic. Let's go ahead and do that. Do you know how we would take this factored thing and get it back into standard form? Boiling. Good old distribution. There we are. I'm not going to always go through the pain of foiling. I'm going to start to assume that you guys know how to and start just showing you what you get when you foil. But for now, I'm trying to demonstrate something. X times x, x squared. X times positive 2i, 2ix. Negative 2i times x, negative 2ix. And negative 2i times positive 2i, negative 4i squared. First of all, the middle terms, positive 2ix and negative 2ix, cancel out. This gives me x squared minus 4i squared. But it would be great if you could remember what I squared equals. Lots of people. I squared equals -1. So that thing at the end says, and I'll show this work for now, x squared minus 4 times -1, which gives me x squared plus 4. There. The quadratic x squared plus 4 can be factored into x minus 2i plus x times x plus 2i. There we go. That's its linear factorization. Both of its zeros are complex. It does not cross the x-axis because it's the parent quadratic that has been shifted up 4 units. So there you go. No x-intercepts. Do you have the ability to solve a quadratic like that? Of course you do. Set it equal to 0, subtract 4 from both sides, take the square root of both sides, bada bing, bada boom, plus or minus 2i. These two things that you just saw in A, x minus 2i and x plus 2i, positive and negative 2i are considered complex conjugates, meaning one is a plus and one is a minus on the imaginary part. Notice, please, that when I multiplied these two things, I ran out of imaginary terms, didn't I? Neat. How when I multiplied those two complex conjugates, I ended up with no imaginary terms. Cool. Also, it would have been great if we could have jumped directly from x minus 2i times x plus 2i to x squared plus 4. That would have been great. And that would have used an Algebra 1 skill that says x plus b times x minus b equals a squared minus b squared. The result should have been the difference of two squares, right? However, we had a I squared in there, which changed it to a plus. We cool in the gang? We good? Okay. Part B. Part B is stepping it up a little bit. 3 zeros this time. And those zeros are what makes the inside of those parentheses equal 0. So I got an x equals positive 5, which is a real number. And then I have positive and negative root 2 I. The I is not underneath the radical. And if it helps you, put a little down stick on it like that so you know that the I is not underneath the radical. One of those zeros is a real number. So what does that tell you? What? That's where it crosses the x-axis. That is an x-intercept. This cubic will cross the x-axis exactly one time. It will happen at x equals 5. How do I know it's a cubic? Because 3 linear factors would multiply to give me an x to the 3rd power. X minus 5, okay. Now, these next two things, x minus root 2i and x plus root 2i, are once again conjugates. So when I multiply those two at the back, and that's what I'm going to be doing, is I'm going to be multiplying these two together first, the result will be what I had up here. Square the front, square the back, put a minus sign in between. And we've done nothing with the x minus 5 yet. Now the two green boxes, or the green box for those two sets of parentheses. Square the front, square the back, put a minus sign in between. Oh, I'm not going to leave it like that, obviously. Let's clean that up a little bit. Just in case you're confused, this exponent is going to be applied to the I and the root 2. Well, what is root 2 squared? 2. And then here's your I squared. And again, I squared, you guys have already told me, equals -1. So what this gives me is x minus 5 times x squared plus 2. And then you would have to FOIL that out. Can I spare us the pain of FOILing this out and just write it for you? Okay, so we can assume that everybody in the room knows how to FOIL. Great. It's going to give us, where am I? Part B. There it is, x to the third minus 5x squared. Don't worry, I'll get out of the way in just a second. Plus 2x minus 10. That's what it'll get when you FOIL it out. I don't know if I have enough vertical space to squeeze C in down there, but we're going to give it the old college try, all right? Before we do, though, for part C, let's go ahead and find the zeros and the x-intercepts. It has 4 zeros, so this would be a degree 4 polynomial once it's all said and done. Hey, look, x minus 3 was listed twice. A multiplicity. My zeros, what makes the inside equal 0? I have x equals 3, and then plus or minus I. Since one of my zeros is a real number, I have one x-intercept at x equals 3. This 4th degree polynomial only crosses the x-axis one time. Neat. Okay. Let's see, you scroll down, see what I have space for. Oh yeah, I can definitely make this happen. Oh yeah, lots of space, yeah. Okay, f of x equals, tell you what I'm going to do. X minus 3 quantity squared. Oh, yeah, the graph would bounce off the x-axis at x equals 3. So it actually doesn't cross the x-axis there, bounces off of it. Multiplicity, even multiplicity. And then I'm going to be multiplying the conjugates x plus I times x minus I. And I want to handle that first, because square the front, square the back, put a minus sign in between is what's going to happen right there. Now this thing, x minus 3 quantity squared, again, I'm going to use an Algebra 1 trick that I would hope, it's not even a trick, a formula that I would hope you know. Let's see where I could squeeze this formula in. Oh, here, how about this? Excuse me. Come on, active board, catch up. I press back. Yay, we're crashing Active Inspire. Okay. X plus a or minus a, whatever, squared gives you x squared plus 2ax plus a squared. This is an Algebra 1 formula. And instead of having the plus, I could have used a minus. Gives me basically the same result. X minus a squared is x squared minus 2ax plus a squared. I'm going to use that for my x minus 3 squared. If you don't know these formulas, feel free to FOIL x minus 3 times x minus 3. It's just a little bit slower, and I would like to not have to do that. The x minus 3 quantity squared is going to give me x squared minus 6x plus 9. Everybody knows how to FOIL. And the green rectangle, square the front, square the back, put a minus sign in between. Square the front, square the back, minus sign in between. And oh look, another I squared. I squared is -1. X squared minus 6x plus 9 times x squared plus 1. Oh boy, wouldn't that just be a fun thing to FOIL out? Everybody knows how to FOIL. Can I just write the 4th degree polynomial that you would get from FOILing? Here we go. X to the 4th minus 6x to the 3rd plus 10x squared minus 6x plus 9. Whew, there it is. So what was the purpose of all of the stuff we just did? Someone in first period was like, I don't understand why we're FOILing these things back out. And I said, well, because I was just trying to prove to you that yes, a string of linear factors will multiply to give you a polynomial with real coefficients. But how did we pull off the result of real coefficients? What happened to all of those imaginary units that we had? Where'd they go? Well, something very special happened. Every time I introduced an imaginary 0, it was accompanied by its conjugate. Pretty neat, huh? You see, the reason why that happened is because complex conjugate zeros or complex zeros always come in pairs, specifically conjugate pairs, every single time. So if you're talking about a polynomial with real coefficients and a and b are real numbers, then a plus bi is a 0. If a plus bi is a 0, guess what else is? That's right, a minus bi. It doesn't have a choice. Complex zeros always come in conjugate pairs. Time to tie it with yesterday's unit. Ready? Remember Descartes' rule of sign? Remember when I said after you find the number of possible positive real zeros, you then decrease that number by 2 each time? This is why you decrease it by 2. Because the conjugate pairs, that's right, are pairs. They come as a set of 2 every single time when they happen. And that is why Descartes' rule of sign has you decreasing by an even number. Neat, huh? Yes? Yes, awesome. Complex zeros always come in conjugate pairs. So we are going to find a polynomial of minimum degree in standard form that has the real coefficients and whose zeros are include these 3 numbers, -3, 4, and 2 minus I. What do you see is a problem with that list of zeros? Something should stand out. There's one complex 0. That's not allowed. So if 2 minus I is a complex 0, what else is? And so is 2 plus I. Its complex conjugate must also exist. So how do we find the polynomial of minimum degree that has these 4 numbers as its zeros? You could FOIL. It would look like this. First and simple, a -3, so that's an x plus 3. Next one simple, a +4, so that's an x minus 4. And the next one, next 2, looks like this. X minus 2 minus I, and x minus 2 plus I. All right. Who's ready to FOIL? Yeah, I'm not doing that. I refuse. And here's why. When you go to FOIL those two brackets down there, you're going to have to FOIL inside your FOIL. No, this is not pimp my math. I am not going to be foiling inside my foiling because I heard I like foiling. No, I'm not doing it. It sucks. It's too much work, and there's too many places to make a mistake, especially with the negative sign. So what am I going to do? I'm going to teach you a way around it instead of what the authors wanted me to show you. Because when I saw that, I was like, yeah, no, that's way too much ridiculous work. So I found a way around it, and here you go. It works like this. Zeros, two zeros, let's just imagine there was only two of them, specifically those two complex conjugates. They happen because of a quadratic that didn't touch the x-axis, don't they? Those two specifically happen because of a quadratic factor that never touched the x-axis. So I thought to myself, if those are solutions, I should be able to figure out the quadratic that produced those two solutions. If I gave you a quadratic that was written in vertex form, could you find the zeros by doing PIMDOS in reverse order? You could, right? I'm going to undo that. Here's what we know. We know that x equals 2 plus or minus I, correct? We know that? That's what the two brackets at the end are telling us. Yeah. Well, time for me to produce the quadratic that creates those two solutions. First, subtract 2 from both sides. Now I'm aware that these solutions came about because it was a quadratic, right? So let's make it a quadratic. Square both sides. I don't feel like doing x minus 2 times x minus 2 because I know the shortcut, x squared minus 4x plus 4. So hopefully you master the shortcut to make this a true quick thing. And on this side, it's just I squared, which is negative 1. Now add that 1 to both sides. It doesn't matter if you square a positive or a negative, you're always going to get a positive result. There you go. The two complex zeros of 2 plus I and 2 minus I come from the quadratic x squared minus 4x plus 5. And we did that without foiling anything. So these two bracketed deals here would have foiled out to be the quadratic that I just found. X squared minus 4x plus 5. So much faster than actually foiling. It's just much, much better. Now the first two, x plus 3 and x minus 4, again, I'm hoping we can all factor. Foil, of course I hope we all can factor too, but foil. And that's going to give us x squared minus x minus 12. The green rectangle we just found out is x squared minus 4x plus 5. And you would finish this up by foiling out all 9 things, looking for like terms, and combining them. Tedious? Yes. Difficult? No. Just be careful, watch for your like terms. Do you need to see me do that, or can I just list out the polynomial? No one's begging to see the foiling, so I'm just going to show you what it would be.
I want to see it.
Really? I mean, I'll do it. Okay.
I wanted to see these two equations.
Okay. X squared times x squared, x to the 4th. X squared times negative 4x, negative 4x to the 3rd. X squared times 5, positive 5x squared. Negative x times x squared, negative x to the 3rd. Negative x times negative 4x, positive 4x squared. Negative x times 5, negative 5x. Okay, suck it in, polynomial. We still have 3 more things to write. Negative 12 times x squared. Negative 12 times negative 4x. Uh-oh, it's getting tight. Negative 12 times 5. Get in there. There you go, minus 60. And then you combine Combine your like terms, which, by the way, are these two. Yay, colors. These two, 3, excuse me. And purple? Yeah, purple feels good. I've got an X here and an X here. I'm sorry, plus 48? Because it's negative 12 times negative 4x. Final result. X to the 4th minus 5x to the 3rd minus 3x squared plus 43x minus 60. There it is.
Made my life just that much better.
I'm happy to do so. What was the hardest part? Do you understand this? Because if you don't understand that, the hardest part will be foiling 2 complex zeros. Yuck.
I would really like to see that.
It's nasty. You're welcome to do it. It really isn't fun. Oh, I'm not doing it. It just kind of sucks. I'm not doing it. So let's do this one more time, but with a slightly more difficult setup. Exact same kind of question, writing a polynomial of minimum degree in standard form, but this bad boy has, that's right, count them up, 5 zeros. Mr. M, only 3 are written. I'm aware. 2 of them are complex, though, which means they have conjugate pairs that must also exist. So you also have x equals 1 minus 2i and x equals 1 plus i. So you've got those 4 complex and that one over there that says x equals 1. You don't want to forget that bad boy. Okay. Here's what it would look like in linear factorization. The one easy one goes right there. And then the other ones, I'm going to have to write small to make sure these fit. I can't even guarantee it's going to fit when I write this small. Did he really just whisper that? I'll let YouTube use their imagination. Yep, told you I was recording these notes. They're going to YouTube. There you go. Oh boy, that is just not pretty. It's just not. I'm not going to foil that. Instead, I'm going to use my trick that I showed you a second ago to do this. And I'm going to do it here as well. I know that x equals 1 plus or minus 2i. I also know that x equals 1 plus or minus I. And it's color-coded. Look at that. They both start the same way. Remember, what we're trying to do is get the quadratic back that produced these complex zeros. So we do that by subtracting 1 from both sides for both of these. They follow the exact same rules. Now we know the plus or the minus is the result of taking the square root of something that was a square. So we need to undo that square rooting. We will square both sides. Again, I would be thrilled if you knew the formula for x minus anything squared. That would be great if you knew it. That way you could just write x squared minus 2x plus 1. And then over here, 4i squared. I'm going to draw a better 4. If the board catches up with me. Come on, board. You could do it. If I hit back again, it's going to try to crash. Yep, there, see? 4i squared. And the one in fuchsia, x squared minus 2x plus 1 equals I squared. You see, it doesn't matter that it's plus or minus because when you square it, it becomes positive. But of course, both of those I squareds equal negative 1. So x squared minus 2x plus 1 equals negative 4. Might as well add the 4 to both sides. and then the fuchsia. X squared minus 2x plus 1 equals negative 1. Add the 1 to both sides. Those are what you would get if you took the time. And trust me, it would take more time to FOIL the stuff in the green box and FOIL the stuff in the fuchsia box. This is faster, believe me. And also, what I'm showing you right here is going to help you avoid using synthetic division with complex numbers, which is something the authors wanted me to teach you. Excuse me while I beat my head against this brick wall. No. No. Not doing synthetic division with a freaking complex number. Out of your mind. That's like doing the math just because you know it's difficult and you want to show off.
That's why we're in pre-calc.
That's why you're in pre-calc? Oh. Oh boy, look at that mess. So yeah, you would have to FOIL all of that out. Apart from not keeping track of your like terms, really, FOILing is not difficult. Would this one be tedious? Oh my gosh, yes. It would have 9, it would have 18 different, wow, 2 hands went up. I must have made a mistake somewhere. Okay, yes. I'm not going to spend the time FOILing this one out. And yes? Shh. What? Yeah, the TI-89 will, but you're not allowed to use it. So anyway, I'm not going to spend the time to FOIL this. FOIL. Will I make you do this on the test? Absolutely. But listen. Will I make you do it with a polynomial of degree 5? No. Why would I make you waste your time? If you can do it with 5, you can do it with 3. You know what I'm saying? I don't have a reason to crush a student like that. Anyway, on my notes, I legitimately wrote FOIL a lot. I didn't even do it. I just wrote FOIL a lot. I did it on scrap paper somewhere else because I didn't feel like wasting all my space. X to the 5th minus 5x to the 4th plus 15x to the 3rd. Suck it in, polynomial. Minus 25x squared plus 24x. Squeeze it in. Minus 10. There you go. Woo. That was a mental workout right there. Apart from keeping track of all your like terms, you should not be finding this difficult. I hope you like my trick of turning zeros back into quadratics.